Good evening, everybody. I'm Sithmi Hevage, a senior majoring in chemistry here at Iowa State, and it's my pleasure to welcome you all here tonight. We would like to thank our co-sponsors for tonight's lecture, the College of Liberal Arts and Sciences, the Chemistry Department, and the Committee on Lectures funded by the student government. Iowa State University, the Committee on Lectures, and the Lectures program do not endorse the views of any guest speaker. A few housekeeping items. There'll be an opportunity to ask Professor Anderson questions. Please note that there's a microphone for you to use set up in the north side of the seating at the front section. Please do not use a flash if you are taking any pictures. If you leave before the Q&A is finished, please exit quietly and refrain from talking until you have left the room. A lectures program student worker will be in the table in the foyer to scan your student IDs if you are here for extra credit. Card scanning will not start until the lecture is finished. All are welcome to stay for an open reception with refreshments as soon as the lecture has finished. Finally, I'd like to briefly announce an upcoming event. On Thursday, October 16th, MIT professor Danielle Wood will give her lecture, How Space Tech is Enabling Sustainable Development on Earth. Her talk will be at 6 p.m. in 2630 Memorial Union. All lectures events are free and open to the public. A full schedule is available on the lectures program website. And now, I'd like to introduce Dr. Pan Sun from the Ames National Lab.
Thank you, Sisimi. Welcome, you guys. It's my pleasure to introduce Benjamin C. Withers, the Dean of the College of Liberal Arts and Science, who leads the most academically diverse college at Iowa State University, and with 21 academic departments, 1 professional school, and over 50 majors, and more than 20 cross-disciplinary programs. The college is a cornerstone of nearly every major offered at Iowa State. At the heart of the learning and discovery, the LAS is home to more than 6,000 students, and more than 40% of all students credit hours at Iowa State are taught by the LAS faculty. In his first year at Iowa State University, Dean Withers implemented a strategic planning process that engages all LAS departments and programs in a focused effort for sustainable growth of the college. Another early accomplishment of his is his leadership in the creation of Iowa State University, University's Center for the Cyclone Civics, created to advance non-partisan civics education and the research on free speech, while addressing long-standing gaps in Americans' civil literacy and engagement. Withers received his master's degree and PhD degree in art history from the University of Chicago, with a focus on early medieval manuscripts. Prior to his arrival at Iowa State, he served in multiple leadership roles at Colorado State University and the University of Kentucky. Now, let's give a very warm welcome to Dean Withers.
So thank you, Dr. Sun, and thank you all for joining us here today. And those of you who are joining us remotely from Europe and Brazil, Dr. Anderson tells me we've got a worldwide audience today. Indeed, I'm Ben Withers, Dean of the College of Liberal Arts and Sciences, and it's my great pleasure to welcome all of you. This evening's lecture is the 39th in the lecture series, which highlights faculty excellence and achievements in teaching, research, and outreach in the College of Liberal Arts and Sciences. Each year, we ask exceptional members of the LAS faculty to present lectures from their own diverse scholarly expertise. They are faculty members who help solve global problems and challenges, who connect art with culture, and who push the boundaries of educational and intellectual dialogue. Over the years, our topics have ranged from an examination of how to improve the way that we meet the next pandemic to explorations of the ways that storytelling can connect communities with policymakers, and to the barriers that people face when seeking mental health treatment. Before I introduce tonight's speaker, I want to acknowledge the ISU Lectures program for their roles in helping us sponsor and coordinate this event. I would also like to thank everyone from the LAS team who was involved in making tonight's lecture possible. This valuable partnership heightens our ability to share the college's contributions with the community, and it's greatly appreciated. So at this time, it's my pleasure to introduce Dr. Jared Anderson, the Alice Hudson Professor in the Department of Chemistry. In his research, Jared applies methods from his training in separation chemistry to tackle critical challenges in a broad range of areas. As head of the Anderson Research Group, he addresses problems as diverse as developing efficient methods of extracting rare earth elements from mining and recycling, detecting pathogens in food, separating and purifying nucleic acids from biological samples in plant materials, and identifying trace-level impurities in pharmaceuticals. Jared's lecture tonight connects the past to the present and looks to the future. He will explore the historic contributions during World War II and extending to current advances that address today's pressing needs here at Iowa State University. LAS research truly does transform the world by addressing the challenging issues of our time, and Jared is no exception. He has won numerous awards, and in 2019 and 2024, he received the Special Creativity Award from the National Science Foundation. So please join me in welcoming this evening's LAS Dean's Distinguished Lecturer, Professor Jared Anderson.
Thank you very much. Thank you very much, Dean Withers, for that very nice introduction. I'd also like to thank Dr. Pan Sun, who is a postdoc, Spedding postdoc fellow at Ames National Laboratory. I'm going to be talking more about his research a little bit later. And also, I'd like to thank Seetmi, soon probably to be Seetmi Hawagi from, she's a chemistry major at Iowa State. She's actually going into her last year at Iowa State, applying to grad school. And so it's really a pleasure for both of you to introduce me today. And I'd also like to thank Linda Kramer. Linda has been great at organizing everything, keeping everything scheduled and on time. So I really appreciate Linda's help as well. As Dean Withers mentioned, today I'm going to talk a lot about some historical aspects of rare earth separations at Iowa State. At that time, we were Iowa State College, before we were Iowa State University. And at that time, we were looking at separating uranium. And of course, I'm going to talk a little bit about why high purity uranium was important. And I'm going to pivot through my talk to some of current issues where we need to be able to obtain secure rare earth elements for a number of our electronics and defense systems that we require within the United States and for living into society. So I like Dean Withers, I enjoy history a lot. I especially like old photographs. And this is a photograph of Iowa State University in 1922. Okay? So to put things in perspective, we have here the Knoll. Okay? So the Knoll, I believe, was built in around 1901. And then we have Lake Laverne. We also have where we're at here, oops, sorry, my pointer. We have the Memorial Union, which was not yet the Memorial Union. I believe that was the old Main. And then we have Beercher Hall. And then we also have, at that time, Chemistry Hall, which is now Gilman Hall. Chemistry Hall was built in 1917. So this is about a few years after Chemistry Hall was built. And you can see here Gilman Hall. We have the Agricultural Engineering Building, which is now where Hogg Hall is. And we also have the Armory, which is still standing. The reason I like this photo is because in about 20 years from when this photo was taken, 20 years later, some really important things happened at Iowa State College. And really it involved a lot of faculty, staff, students working together on a really important national problem that, again, is isolating uranium. And one of the important figures in this was Professor Frank Spedding. So Professor Spedding was born in Canada. He obtained his bachelor's degree from the University of Michigan and his PhD in 1929 from the University of California, Berkeley. And he started at Iowa State College in 1937. So you'll notice that there was about a 7 or 8 year gap between the time he got his PhD and he started his position. And if you look at the time, this was right at the beginning of the Depression. And one of the big challenges was actually finding a job at that time. Despite the fact that he worked with a very famous organic chemist, Gilbert Lewis, who a lot of the students that are taking organic chemistry, I know there's some of them in the audience, the founder of Lewis Dot Structures. He had a very strong training, but there was a challenge of finding jobs. He was offered a position here at Iowa State, where he became a professor of chemistry in 1937, and then later, after the Manhattan Project, became a professor of physics and a professor of metallurgy. He was actually the first director of Ames National Laboratory in 1947. We have our current director, our newest director, Dr. Carl Mueller here. So this was our very first director of Ames Laboratory, and he served as director from 1947 to 1968, which is a very long tenure. Another very important figure that I'll talk a lot about today is Professor Harley Wilhelm. And Professor Wilhelm actually was born in Elston, Iowa, and he attended Drake University. And he was a fantastic athlete. In fact, he's listed as one of the top 100 athletes in the history of Drake University. And he joined Iowa State University in 1937 after obtaining his PhD in 1931. And he was an assistant professor of chemistry in 1940, associate professor of chemistry in 1944, and a professor of chemistry in 1945. And he was really credited with a lot of the day-to-day operations of what I'm going to be talking about in the using high temperature reduction reactions to actually isolate and purify uranium. He was the associate director from 1947 to 1966. So Professor Spedding spent a lot of time on the road. It has been stated in many literatures that he spent every couple weeks, he was traveling, I presume by train at that time, to Chicago. And Professor Wilhelm was really kind of the one keeping the trains going in Ames and making sure that the project deadlines were being met. And this kind of gets us up into the discussion of the Manhattan Project. And I think we're all familiar with the idea of what happened with the Manhattan Project. So this comes on the heels of the nuclear fission being discovered and really theorized by really 4 scientists, Otto Hahn, Fritz Strassmann, Lisa Meitner, and her nephew, Otto Frisch. And that was in 1938, okay? And we all know about the very famous letter that Albert Einstein wrote to President Roosevelt, encouraging him to take action on using the nuclear power, the power that can be harvested from the atom to really intercede with the war that was happening, that was ravaging the world. And in 1941, President Roosevelt approved the atomic energy program, and this really started a lot of the studies into purifying uranium, plutonium, developing reactors, testing whether or not the theory that had been developed could actually be implemented. And in order to achieve the self-sustaining chain reaction, Fermi at the University of Chicago predicted that this could happen, but it required high purity uranium. And at that time, there were about 4 mines in the world that had uranium. And there was a lot of uranium, so that wasn't an issue. The issue was getting the Allies getting access to that uranium, the stockpiles, so that they could actually start to do that purification process. In 1942, the Ames project began, and this was directed by Professor Spedding. Okay? So this became the Ames project, and this was really an offshoot of a metallurgy project from the University of Chicago. And so this was the reason why Professor Spedding spent a lot of his time on the road to update the team because he was really involved with a lot of administrative aspects. And so the Ames project was a very important part of this, as I'll describe in a moment. And so here we have an image of the nuclear fission process. So taking uranium-235, we have a neutron to form an excited uranium-236 atom. This uranium-236 will undergo fission, and what we're really looking at is the amount of energy that's being produced, also producing 3 neutrons that can cause this chain reaction to occur. And there's a lot of really interesting diagrams that you can uncover, for example, from Robert Sieber's group at the University of Illinois, where he was actually looking at the assembly of the early prototypes of the bomb. So as I mentioned, there was a need for high purity uranium. And this is a form of chemical separations that I'm going to talk a little bit about in more detail. So I'm a separation scientist, and my graduate students and postdocs that are here in the audience, they're also all separation scientists. And our job is oftentimes, as Dean Withers mentioned, to take complex mixtures and oftentimes break them down into smaller, more pure components. And this is something we do on a number of different applications. You know, Dean Withers mentioned purified nucleic acids, and we use this also in rare earth separations. And we're oftentimes doing this by taking advantage of the unique physical and chemical properties of molecules, ions, and compounds. And some examples of chemical separations are extractions, distillation, which is very, very important in the petrochemical industry, precipitation, recrystallization, chromatography, electrophoresis, and chemical reduction processes. And it's really this chemical reduction process that I'm going to highlight that was really pioneered here at Iowa State College, Iowa State University, for the purification of uranium. So this is the Ames process. So as I mentioned, the Ames project was really the idea of separating high purity, being able to achieve high purity uranium. And when I mention high purity uranium, we're looking at 99.1% and higher, okay? Mining uranium and then purifying the uranium to get to these levels. And really, what's really interesting is looking back at the history of this. Professor Spedding and Professor Wilhelm developed these bombs, okay? Now, in chemistry, we talk about bombs, like bomb calorimetry. Many of you have probably had a lab on bomb calorimetry for the students in the audience. But what Professor Spedding and Professor Wilhelm were working on is on the graph here, on the picture on the left, they're taking some sort of capsule, they're putting this into a bomb. This capsule is going to have uranium tetrafluoride with magnesium or aluminum. So in this case, this is a high temperature reduction process to reduce uranium-4 to uranium-0, okay? But in order to do this, you need to heat this up to a couple thousand degrees Celsius. The original bombs that were developed were nothing more than taking a piece of metal, a tube, welding one end, putting the uranium tetrafluoride and magnesium in the other end, and then sealing this up using welding, and then heating that up to higher temperature. Eventually, they refined this so they could actually scale this up so they could produce more of the uranium. As soon as the bomb, this high temperature reaction happened, this reduction process, the middle figure here shows, or the middle picture shows the slag that was formed on the outside of the inner outside of the bomb. And then what was left is actually on the inside what they called an ingot. And this ingot would be the pure uranium. And you can see here from this picture that I found on Ames Lab's website, this ingot was 99.05% pure. Now, there were different ways that they achieved that purity or measured that purity. At that time, they were using techniques like flame emission spectroscopy to actually measure that. As I'll talk about in a moment, some other techniques were developed here at Ames Lab that really allowed them to measure this purity even more. So more than 2 million pounds of pure uranium were produced during the Ames project. And even some of this uranium that was purified was used in the first prototype that took place at the University of Chicago under the stadium, where they actually did the first test. After the war and the conclusion of the Manhattan Project, Ames Laboratory was officially formed in 1947 by the US Atomic Energy Commission. And research still goes on. There's still a very highly concerted effort towards rare earths. I'll talk about some of those today, but also towards different materials chemistries. There's many different research areas. And a lot of these originate from the really spectacular work that was done at Iowa State University and then later the National Laboratory during World War II. In the 1960s, the Rare Earth Information Center was established, and this really allowed people to get more access to purified uranium, purified rare earths, learning different ways in which these rare earths form different complexes and so on. And as I'll mention, this really catapulted into the chemistry department because many subdisciplines formed. For example, solid state chemistry. I know Professor Miller is here in the audience. So solid state chemistry started with, at Iowa State, really with Dr. John Corbett, Bob McCarley, and then later Professor Miller and so on. Many important contributions came to Iowa State University also because of the work that was done in World War II. Since I'm an analytical chemist, I look back and I know that there were many research areas that were also catalyzed by this important collaboration between Ames Laboratory and Iowa State University. One of the biggest areas in chemistry that Iowa State is very known for, traveled a lot internationally, and almost always when you're at a conference, someone sees you're from Iowa State University, they say inductively coupled plasma. This is where the inductively coupled plasma was developed by Professor Vilmor Fassel, Professor Harry Sveck, and Professor Sam Hauk. And inductively coupled plasma allows this source operates at extremely high temperatures, 5,000, 10,000, on average about 8,000 Kelvin. And it allows us to, is a perfect atomization and ionization source, and can be used in mass spectrometry. It's one of the most widely used methods of analysis all over the world. And this was developed here at Iowa State really after the Manhattan Project. And as I mentioned earlier, the need to determine the purity of that uranium, that 99.05% uranium, that's something that can easily be achieved using the inductively coupled plasma and with extremely high sensitivity. And the work also gave rise to many new generations of separation scientists. We've already mentioned Professor Spedding, but Professor Spedding, after the Ames process, using the thermite reaction to get pure uranium, he developed ion exchange methods for performing rare earth separations. And I really like this photo because he's standing in front of a chromatography column that's packed with the ion exchange resins that his group developed. And he is really known for many things, but the ion exchange methods that were developed to achieve very, very high purity rare earths, not just uranium, but other rare earths in the periodic table. Professor Jim Fritz, who developed many methods in separating ion separations and ion chromatography. And again, this was all related back to the Manhattan Project, where developing methods to separate ions, metal determination. I've met some of his former students, and they tell me that they used to have to know all of the different ligands that complex different metals. He was really designed and developed a lot of those in his career. And then Professor Ed Young, who was trained as a spectroscopist, was one of the very first to use lasers in spectroscopy. But at Iowa State University, in addition to looking at doing single molecule detection, he also used capillary electrophoresis and chromatography and really developed his research in a lot of areas of separation science. So now we look at today. As I mentioned in the past, separating uranium was an important issue for wartime, the development of the ways in which the national labs could work together. But now we have another challenge, and that's securing critical materials. And this is something we hear about every day on the news, okay? And I wanted to kind of define a little bit critical materials and rare earth elements. So critical materials are actually designated by the Secretary of the Department of Energy. And these are materials that are used for different energy applications. And you see here, these plots show the supply risk on the x-axis, and on the y-axis, the importance to energy. The one on the left is showing us our short term from 2020 to 2025. And you can see a number of these critical materials. The ones in red are the really critical ones: dysprosium, terbium, neodymium, gallium. A lot of these are what I'm going to be talking about today. And then if we look on the right, we have the medium term. This is going from 2025 to 2035. And what you see is many of those, we see many more of those critical materials, I should say many of those that are either near critical or not critical, going into the critical category. And many of these are going to be our rare earth elements, I'm going to define in a moment. And so really there's a very important initiative taken to develop new ways to harness these critical materials, both from how we mine and secure these from the environment, but also how we recycle our cell phones and different components that have these rare earth or critical materials within them. And this is all information that's obtained from the National Energy Technology Laboratory, NETL, at the US Department of Energy. And then we get into rare earth elements. Rare earth elements are important because rare earth elements are used in a lot of the electronics that we use on a daily basis. And I'll kind of show some of those in a moment. But rare earth elements are lanthanides. And you can see here from the periodic table, we have 15 of these, ranging, shown here in the light orange and dark orange. And then we have scandium and ytterbium. So there's altogether 17 that we consider rare earth elements. And these rare earth elements are extremely challenging to separate because once you put these in water, they form ions, if they're the +3 charge. And the size of these ions, when they're hydrated by water molecules, they have very similar shape. These have very similar sizes. And so it's very challenging to actually separate these rare earth ions in a solution. I always use the example of a bag of Skittles. The bag of Skittles with different colors, those would be the rare earth elements. But when we put these in water, they have very similar structure. We can separate the Skittles by looking at the color, but when we try to separate the rare earth ions, we're trying to do so in a chemical basis. We try to use different chemical methods to actually separate these rare earth elements. And a lot of these I'll highlight today. So some technologies that require rare earth elements are shown here. And so this is where we hear a lot about this because rare earth elements are used in many, many different areas. And what I really like about this figure from NETL is it shows the different types of applications, but also highlights the type of rare earths that are oftentimes used. So magnets. Magnets use a lot of rare earth elements. And we see this a lot, especially nowadays. We're looking at ways to recover and the different types of rare earths that are within magnets. But these aren't just hard drives and magnets we use like for MRIs and so on. But these are even magnets that are used in your brakes on your car. Okay? There's rare earth elements that go into that. There's metal alloys that are in your batteries, whether they're your lithium-ion battery in your phone or the batteries in your car. Defense applications. A lot of our communications require rare earth elements in order to have communication for different military vehicles and so on. Also catalysts. Catalysts are important because we need to be able to have ways to purify fuels, make fuels. All of these are done by using catalysts, glass polishing, ceramics, phosphorus, many different applications of rare earth elements. So one of the biggest mines for mining rare earth elements is actually in Mountain Pass, California. This is in Southeast California, about 35 miles or so from Las Vegas. And this mine is actually the only mine right now in the United States where we're actually mining rare earths. And this mine had kind of been shut down for a period of time because it really wasn't very economical to mine rare earths. The largest, the most commonly, the most abundant rare earth that's actually mined in the Mountain Pass is actually neodymium. But all of the rare earths are present within this mine. And one of the challenges is that it's, as I'm going to show in a moment, rare earths are not rare in the sense that there's not much of them. The reason they're called rare earths is because when we find rare earths, they're intermixed within a lot of minerals. We actually have to have separation methods to remove them from the minerals and then purify them. It's not like digging metals from a mine where you can find those metals in relatively pure form, segregate in pure form. These we actually have to remove these from minerals, and that requires an extensive separation process. And that separation process is highlighted here. Okay? So the very first thing is we have minerals like basanite that actually is an excellent source of many of these rare earth elements, and these are found within the mines, such as at Mountain Pass. And the first thing you need to do is you need to dissolve these minerals to get access to those rare earth ions. So what's commonly done is that these minerals are actually dissolved in an acid solution to do a leaching. So leach the rare earth ions out of these minerals to get them in a relatively pure form. And that actually gets them, these are typically found in an oxide form, a rare earth oxide. This leaching process gets them into an ion form. And then the really messy part is this liquid-liquid extraction process, okay, that's shown in B. So in B, we're now looking to separate those rare earth elements through this liquid-liquid extraction. This organic phase is going to be some sort of oily phase. And then we have our acid leaching solution that's going to have our rare earth ions. And within this system, we're also going to have ligands. These are organic ligands. These ligands will bind selectively to these metals. And once these ligands bind, those rare earth ions are going to partition to the organic phase, and we can recover this. But this is a very messy process because it's not like you just put all these metals here and it happens that they're all separated, all 17 are separated. Some of them are very difficult to separate, namely the lights and heavies are more challenging to separate because we're relying on these really intricate interactions between these ligands and solubilities. And so this process, it can be very time-consuming, consume a lot of solvents, and we also have to worry about the waste. And it's something I'm going to be talking about, highlighting Dr. Pansun's work, where he's actually combining a lot of these workflows so we can actually improve the remediation process. One of the big challenges is a lot of these processes can cause a lot of environmental concerns because they're not totally sustainable. But it's the best way we have right now to purify large quantities of rare earths. Okay. Now, I really wanted to mention the Critical Materials Innovation Hub because the Critical Materials Innovation Hub was established here at Ames National Laboratory in 2013. And this brings together a large team of interdisciplinary scientists. with a lot of expertise to solve these very challenging problems. And we know from just like the Manhattan Project, that project was successful because bringing in chemists, physicists, engineers to solve very challenging problems. And so that's one of the things the Critical Materials Innovation Hub does. It brings together scientists from 9 national laboratories, over a dozen universities, and 30 industrial partners to really address a lot of the challenges in mineral processing, manufacturing, substitution, the efficient use of critical materials, as well as integrating scientific research and engineering practices to really improve the engineering and sustainability process. And there's been a lot of very exciting work that's been done in the Critical Materials Innovation Hub. I don't have time to talk about all this, but if you have time, it really is a great asset here at Ames Lab to have this, because it's a very important, solving a very important societal problem. So now I get to talk about some of the really fun research that is being carried out at Ames National Lab and Iowa State University. And I wanted to highlight Tanya Prozorov. Tanya, Dr. Tanya Prozorov? Okay, so Dr. Tanya Prozorov is here in the front. So Dr. Prozorov led a project and is leading a project. This first initiative of this project was looking at kaolinite. These are ion exchange clays. So as we saw from this former slides, we have minerals that are naturally very good at capturing rare earth ions. So in this first project, Tanya's team was working on understanding these interactions. Why is it that these ion exchange clays can coordinate these light versus heavy rare earth ions? And what can we actually learn from this coordination so that we can look at developing new methods, new materials that can also coordinate these rare earth ions? And this serves as a great way to actually develop new ways to separate these materials. So Tanya's team, really, these were the foci of the team, looking at the rare earth elements, designing new platforms. Some of these platforms that were developed by Professor Wenyu Wang from the chemistry department with MCM22 materials. These were clay mimic materials to coordinate to the rare earth elements. And we had computational expertise from Professor Jim Evans from the physics department at Iowa State, as well as Dr. Sean Kaufman from Pacific Northwest National Lab. And as soon as these rare earth ions can be captured by these materials, we look at different ways to actually selectively strip these rare earth ions out of these materials. And that's where Professor Windus, Teresa Windus, the chair of chemistry department, and my group came in to actually develop new ways to selectively strip these rare earth ions. So once you have a material that can actually capture these rare earths, how do we remove these one by one? Because remember, we have altogether 17 rare earths, and we want to be able to separate them in a one by one, so we have different piles of all these rare earths. And so the second part of this project, this is now the second year of this project led by Tanya, is now expanding our understanding of this interaction of rare earth ions with clays and clay mimic materials, and is expanded to 2 fantastic scientists, Dr. Fred Praz, is Fred here, and Dr. Julia Zakina, is Julia here? Okay. So Julia and Fred, so Fred has expertise in solid state NMR. So Fred's group basically can use NMR techniques that actually understand where these rare earth ions are being captured within the material, and allows us to look at interfacial effects. So when these rare earth ions interact with the material, they do this through interaction on the surface, but then they can also intercalate into the material. And nuclear magnetic resonance is exactly like your MRI techniques we have in the healthcare setting, except for the NMR really allows us to control over understanding where these rare earth ions are within the material. And then Professor Julia Zakina's group develops, her students, Rain and Rabul, developed methods to produce a really fascinating class of materials called layer double hydroxides. And these layer double hydroxides are very similar to the clays that I mentioned, like kaolinite and basanite, and how they have a space, an interlayer space, that can actually capture these rare earth ions. And so we work together with these teams to actually still understand how we can, once these rare earth ions are captured, how can we remove these rare earth ions selectively to achieve this separation. I think I see Rabul in the audience there. So what's really great about these projects is we can work with scientists at Ames National Laboratory, and we have access to techniques like Tanya does a lot of work in TM and SEM techniques. These are instruments that you don't find at universities. You also don't easily find DNP NMRs at universities, or you might find them, but you don't find people like Fred Pross at university settings. And this really allows us to work on very challenging problems that cannot easily be tackled with, at universities. So there's really a lot of exciting work being done within the two projects led by Tanya. This is some of the most recent results that we've published, or that we've got submitted. So this is showing as I mentioned, we have ytterbium and neodymium. Ytterbium being, and neodymium being our light versus heavy rare earths that are captured by the kaolinite. And once we capture the kaolinite, we want to understand what are ways in which we can selectively remove these rare earths. And so my group has used these deep eutectic solvents, and these deep eutectic solvents have a lot of flexibility because depending on how we make these solvents, we can impart different properties into how they coordinate to these metals. And there's really a lot of tailorability in how we design these materials. And we've developed materials, or deep eutectic solvents, that allow us to strip certain metals, different rare earths, from the kaolinite substrate versus others. And we've got some very beautiful images from Tanya and Tanya's group. I want to also highlight Dr. Pansoon's work because Dr. Soon just started, this is his end of his first year at Ames National Laboratory. He's already done a lot of very exciting work on how we can actually remediate rare earths. And so this is actually what the Department of Energy likes to see. At the very top, you have all of these rare earths in nice piles. That's eventually our goal, is to be able to take complex streams and isolate all these rare earths from light to heavy. On the left is the traditional liquid-liquid solvent extraction process. So this is the process I described earlier, where we have the ligand and the organic phase and the water phase, okay? And then this is the industrial wastewater that's produced, okay? This industrial wastewater is very, as you can see, there's a lot of dirty, but it's a very messy business. And in addition, this wastewater has ligands that were not completely recovered, okay? This wastewater is not something that you can just let off into the river, the rivers around Ames. So these are some big challenges, and we want to be able to develop these methods so that these extraction and recovery methods are more sustainable. And we not only want to use this for mining, but we eventually want to be able to recover the rare earths that are from your cell phones, from your computers, and so on. And so what Dr. Soon did was really cool technique, really cool approach. So as I mentioned, we have the liquid-liquid solvent extraction. We highlighted that earlier. We have a ligand molecule that's hanging out in these streams. These are not totally recovered, okay? So that water phase still has ligand left over. And instead of dealing more with that, he's using that on another approach. And this approach is to look at spent magnets. So these spent magnets would be magnets that are left over from, that we might throw away into the landfills. These spent magnets can now be leached to remove these rare earths. And then he's using this wastewater to actually precipitate out the rare earth elements from the spent magnets. And so this is using those remaining ligands. Instead of getting rid of that and having to synthesize new ligands, we're using that to precipitate those rare earths. And then this becomes a cycle. Now we can recover those ligands from this precipitation reaction, and now we have a way to precipitate both the rare earths and the transition metals using methods like oxalic acid. As I mentioned earlier, Professor Fritz, he would be very excited by this because oxalic acid was a very common way in the 1950s and 1960s to precipitate out metals. So this process developed by Dr. Sun allows us now to really combine liquid-liquid extraction with methods of dealing with rare earths from magnets so that we have a lower environmental impact in these separations. And then my group is also working in methods to use 3D printing. So I see Daniel and Indunil here and Emma. So there are three working on ways to use 3D printers to actually make different polymers that can actually be used for separating these materials. So this is a 3D printer here. So it looks like it's printing at the Eiffel Tower. Okay. I had a student, one of my students was from Taiwan, so she was always printing Taipei 101. But that's definitely, I think, the Eiffel Tower. And so Daniel has really developed methods to take commercial printers, modify these printers so that we can use very small volumes of a formulated reaction mixture to print resin materials that we can use to extract rare earth elements. So the advantages of 3D printing is you can quickly prototype a sample, it's cost effective, and it's highly versatile. But the limitation of commercial printers is you need to have liters, oftentimes a liter of your reagent that's going to be your pre-polymer to print your material. And obviously, we don't want to have to make synthetically liters of reagent to print. We want to work on microliter or milliliter scales. And this also, some other limitations are material costs and production of material waste. And so what Daniel and former student Shuan, who's now graduated, she's probably listening, they've developed, taken a commercial printer and modified this printer, the build plate of the printer, so now we can print milliliter volumes. We just place these reaction mixtures into this Petri dish or these six-wall vessels. And so each one of these vessels has a different pre-polymer mixture that's synthesized. We're only talking about a few milliliters, even down to the microliter volume. And now we can print on each of these build plate platforms, the type of material that we want to actually make into a polymer and test for rare earth extraction. So this really allows us now to think about ways to use customizing with 3D printing to make polymers that can be used to capture rare earth elements. This is a big advantage. It could have a big advantage because with a solid, you can recover the rare earth, strip the rare earth, and then reuse the polymer again to do extraction and stripping subsequently. And so this is something that we're really excited about in developing these printing platforms. So I would like to, first of all, thank again Dean Withers for inviting me to present today on some history about Ames Lab, I should say Iowa State College, the work that was done at Iowa State College, and then the creation of Ames Lab, and really talking about the way in which an enormous amount of effort of scientists and engineers came together to solve a very important problem. And the same thing is happening today with our need to secure rare earths and critical materials. And I really want to emphasize the unique relationship between Iowa State University and Ames Laboratory, and the fact that we're really lucky to have the symbiosis between these two entities because we have this ability now to tackle very big problems. And we also have students that get to be involved with these research projects. And that's a great opportunity for them to develop understanding and use their creativity to address very important societal problems. And so a lot of what you'll see, what you are seeing with Ames Lab, the Critical Materials Innovation Hub, and the research I presented today are ways in which we're trying to address capturing rare earths, critical materials, so that we don't have to keep mining these and eventually being able to recycle these as well. I'd also like to thank my research group. This was the most recent photo I found. We were saying goodbye to Siwang, who left to go back to China. And I'd like to thank the sponsors of research in our group. And I'd also like to thank Alice Hudson. I know Alice is listening, and I think her sisters are listening from Minnesota, because she actually sent me a message today, this afternoon. So thank you very much to Alice Hudson. She's been a tremendous, supporter of the chemistry department at Iowa State, as well as the college and the university. And so very much thank her for her tremendous generosity. She supports a lot of undergraduate and graduate student activities also in our department. And thank you again for listening.
I want to see if there's any questions at this time. We have some time before reception begins. Anyone with a question for Dr. Anderson? Would you like to come up to use the microphone, please? See what you volunteered for. Should be. No?
Okay, I can speak loudly. I just wanted to know how you originally got interested in this field and what made you come here to Iowa State and participate in it.
So what was your name again?
My name's Caitlin.
So Caitlin's question was, how did I originally get interested in this field, and why did I come to Iowa State to do this work? So Dean Withers might have mentioned that I actually got my PhD at Iowa State University. I worked with Dan Armstrong. I didn't talk about him because he was only here for 5 years, but he worked a lot in chiral chromatography, so separating chiral molecules, enantiomeric molecules. And so when I was working in his group, I was involved in a lot of really unique projects. My first project was actually trying to isolate the pheromone from brown recluse spiders. So we had all these spiders roaming around the lab. Probably Dr. Miller doesn't know that. He was probably chair around that time. So we were trying to isolate these pheromones. And I was really intrigued with the ability to tackle unique problems. And I then started my career at the University of Toledo, the same place where the football coach, Matt Campbell, came from. And while I was there for 10 years, I really developed a research program looking on different ways to capture nucleic acids and so on. And upon coming back to Iowa State, as I mentioned, there's a tremendous legacy of separation scientists that pioneered new areas. And so that's been an exciting thing. And then we get access to great students that also bring a lot of ideas, like the 3D printing. I'd heard of 3D printing, but until Shuan and Daniel, many times they would have meetings with me, encouraging me to open up the Workday account, to buy certain things. So it's, that's a great aspect. And I think another big advantage is being able to work with researchers like Tanya Prozorov and Fred Pross in Ames Lab, where we, again, have different expertise to really look at problems differently. I think that's a really important thing, as science today is very interdisciplinary. I think the days are gone where one scientist solves a problem by themselves. Really, our problems now are too complex. And so I enjoy learning about new things. And so I think hopefully that answers your question.
Looks like we have another question.
for your lecture. My name's Tom Walsh. I'm an alum from Iowa State. There's a company here in central Iowa that they take discarded hard drives and they're extracting rare earth materials. Is that a feasible process?
I guess it would probably depend on the method they're using, but I think that that kind of gets into the magnet leachate work that I was talking about. I think that, you know, probably when you're looking at how many hard drives they're separating, I think all of these probably add up. But a lot of it is the methods you require to get access to these leachates, whether they're acids or so on. I know the Critical Materials Innovation Hub, I believe, has an acid-free process that they use, which is really a fantastic method. So I think there's a lot of, I think that's important to do the recycling.
Thank you.
Any more questions?
We have a question here.
Thank you for speaking to us today. My question's a little bit more generic, but when you're coming up with research like this, what's your inspiration or starting point? Is it your interest in chemistry? Is it specifically the extraction and isolation process, or the applications, the problems that you're trying to solve?
Very good question. I think a lot of things are driven by a need, a societal need. So for example, a lot of my students are working on projects that are, for example, the nucleic acid work. There's nucleic acid chemistry has skyrocketed now that more and more drug companies are using nucleic acids as therapeutic agents. So there's a greater need now to separate nucleic acids than there was 10 years ago. There was still a need, but now the need is even more compounded because the nucleic acids have very similar structure. So I think a lot of that, to be honest, a lot of it goes when going to conferences. You know, we travel a lot to scientific conferences where we get to interact with our peers. And when you go to a conference in Europe or you go to a conference in South America, you're oftentimes exposed to challenges that we may not have here in the US. Or ways in which they may be addressing those issues. So I think a lot of it goes into the need, and then the curiosity. Are there ways in which we can use different methods to solve those problems? And I think, you know, since I'm a separation scientist, if you look at those Spedding, Professor Fritz, and Professor Young, you know, all three of them were working on very different types of separations, but they all were targeted towards, you know, different applications. Like Professor Young developed a method called a multiplex CE instrument that actually helped accelerate the Human Genome Project. And so I think there's, you know, he would probably say there's a timing. I believe he wrote a really nice article that said a lot of it is the timing of some of these activities. But I think for my recommendation to students is read a lot, attend lectures, and you know, when you go to conferences, go to the talks and hear about what some of the challenges are and how you can actually help.
Awesome. Thank you.
So it's 7 o'clock. Let's stop here. If you have further questions, we have a reception. Come up to Dr. Anderson later. Before you leave, I'd like for you all to join me one more time in thanking Jared for his talk. I'd also like to give a shout out to Alice Hudson and her family who are listening tonight. I didn't know that they were. Thank you for letting us know. Alice is a wonderful person, and it's her generosity that allows us to have professors like Jared here. So thank you, Alice, for that. Watch for future events in this space. We'll continue to work with lectures and sponsor lectures like this. In the spring, we'll have another Dean's Lecture. If you want to keep up with events in the College of Liberal Arts and Sciences, please visit our website. Of course, that's las.iastate.edu. Have a good evening and enjoy us for our reception.